Hi, welcome to Concept Based. I'm John Hepworth. This is Year 11 Advanced Introduction to Differentiation, and we're looking at another rule today. Now, this is the second of the rules, well, sort of the third of the rules we've looked at. If you haven't seen the previous rules, such as the product rule, then go back and watch those videos. But this one is about the next one in the series, which is called the quotient rule. Now, as I mentioned in the product rule, particularly if you're the sort of math student who really wants to understand why something happens, I would go and actually go into an AI program that you have access to. I use Copilot and say, show me the proof of the quotient rule. And it will go through the whole first principles of how the quotient rule actually works. And for some of you, that's necessary because you want to get to a situation where you're like, I accept that this rule is true because it works a particular way. And there's always the mathematics there to back up why a rule is a rule. So if you are that sort of student, I definitely recommend putting that in there and writing and seeing what the full work solution is so you feel comfortable that the rule is the rule. If you are the student who is like, just give me the rule and I'm just going to use it over and over, awesome, that's fantastic. But what we want to take into consideration is ways that we can remember the rule. So I mentioned in the previous video about the product rule that people might use rules like VUV. So again, you might use some sort of mnemonic or way of recalling the rule. As I also mentioned in the product rule video, I remember this rule just as a big long sentence. So let's get into it and I'll show you the rule. So you can see in this function, we have a new situation for doing differentiation where there's a fraction. Not just that there's a fraction, because if we had a fraction where it was like 3/2 lots of x, then that fraction is just a value, it's just a number, and we can just differentiate as normal. But what I'm talking about is a fraction where there is a function on top of the fraction, in this case root x, and a function on the bottom of the fraction, in this case x squared minus 1. What do we do then? Okay, so the rule that we're given is that if we have, or I might use f of x because that's what we've got here. If we have a function where it is one function over another function, then the derivative of that function, now you might be surprised by this rule in its complexity, is the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function all over the bottom function squared. Now you might have been thinking, oh look, I don't care why it works, John, just tell me and then I'll use it. And now that you've seen it, you might be like, what? That's crazy. That's like a lot different to what I possibly expected it to look like if I was just going to differentiate it. So once again, maybe chuck it into AI and have a look why the proof is what it is. So we've got this. Now, students will mess this up because this one has a subtraction in it. And, you know, we can't put things in the wrong order when we've got a subtraction. 5 minus 3 is 2, but 3 minus 5 is -2. So you have to remember that it's the bottom times the derivative of the top minus the top times the derivative of the bottom. And just like the other video, and just like I said at the start here, I say that sentence in my head every single time I do one of these entire quotient rules. The bottom times the derivative of the top minus top times the derivative of the bottom all over the bottom squared. I'm always saying that. But here it is in a rule form there for us to use as a quotient rule. So let's go ahead and apply this rule to the function that we've got here, which is root x over x squared minus 1. Okay, so our derivative is going to be the bottom, so x squared minus 1, times the derivative of the top. Now we've done the derivative of root x before. An easier way to deal with root x is to think of it as x to the power of a half. So the derivative of that, I'm just going to put this in brackets because it's multiplying two terms. It's the power times the front, drop the power by 1. So a half minus 1 is -1 on 2. Minus the top, so our root x, times the derivative of the bottom. Now the bottom, we had x squared minus 1, so the derivative is 2x. The minus 1 is a constant, it does not appear, so we have 2x. That's a terrible x, and I'm running out of screen here. All over the bottom squared, so x squared minus 1 all squared. Now, it is done. We have done the derivative, but some people won't want to leave it in that form. You'll want to tidy it up as much as possible. How can we simplify x times root x? How can we rewrite x with a positive index? So we might need to do another fraction. And people might want to make it as tidy as possible. But in this case, we really don't need to, because what we're being asked is to evaluate the derivative at x equals 3. So we can just go and substitute in to our derivative the value 3. So I'm going to go and do that. So now I'm going to do 3 squared. I'm going to do that in one hit. So 9 minus 1 times a half. Now it's 1 over the square root because it's negative indices. So I'm going to write times 1 over root 3 minus root 3 times 2 times 3 is 6 all over 3 squared again is 9, 9 minus 1 is 8, 8 squared is 64. And I'm going to just go and chuck this in my calculator and get a value for the derivative at that point. Am I going to chuck it in my calculator? Yeah, it's got a root 3. I mean, I could be tidy and go for an absolute value. 8 times a half is 4. So 4 over root 3 minus 6 root 3 over 64. And let's take this opportunity to do a little bit of fraction work and tidy things up. I'm going to times the right part of the numerator by root 3 so that I can make it all over root 3. And I get 4 minus root 3 times root 3 is 3. 6 3s are 18. And now that is all over root 3. And then it's all over 64. So it's actually all over 64 root 3. And then 4 minus 18 is negative 14 over 64 root 3. And then we're just going to look for the largest number that's going to go into 14 and 64, which I think is just 2, because then we get down to the prime number 7. So negative 7 over 32 root 3. Some people might not like that as being like an exact value answer because they want to rationalize the denominator. I'll go ahead and do that for you. Negative 7 root 3, 32 times 3, so 96. And I'm pretty sure 96 does not have 7 as its factor. 77, 84, 91, 98, it is not a factor of 96. So negative 7 root 3 over 96. Now, would we ever, when I talk about concept-based, would I ever have sketched this function first and tried to work out whether or not I would have had a negative gradient at 3? You know, like, does all of my calculations, do I have any way of checking it? Maybe I would have. Probably I wouldn't have, but maybe I would have, just to see if I can have some sort of idea of what I'm doing. If I was going to do that, what would that even look like? So if I have f of x equals root x over x squared minus 1, I can break that denominator up into x minus 1, x plus 1. And so you can see I've got this parabola at the bottom, and I've got root x at the top. So root x at the top means the domain's going to be restricted to being just positive, because root x is positive. So I've got this root x part that goes like this. And then I've got this parabola that goes through at negative 1. And we really only care about the positive part of it because that's the only part of the domain that exists, because otherwise we get a negative in the square root. And then we're doing the top one divided by the bottom one. Now, again, I've mentioned you'll do this further in your course. You'll have an idea of what's going on in the future. But what I do know is that 0 divided by anything is 0. So my graph is going to start here. I'm then going to have, up until this section, I'm going to have positive values divided by negative values. So I'm going to have a negative answer. But up here, we end up running into a problem where the denominator is 0. You know, if we put 1 into here, up here, we'd have a 0 in the bottom. So we're going to have some sort of asymptote here. Now my graph's getting messy. So it's going to be heading down into this direction. And then I'm going to have a positive part coming down, and it's going to get smaller and smaller. So it's somehow looking something like this, right? Not exactly, but I'm just roughing it out. And why am I roughing it out? Because I know that this is happening at 1 and this is happening at 3. And look, here's my negative gradient that I should be getting at 3. Now, I'm going to say it again. Would I ever do that in an exam to check that my answer's correct? No. Like, the amount of time that took me and the level of accuracy that I get from the checking is not there. But I got to do a bunch of things. I practiced my surd simplification and exact values as I did my derivative here. I then went and practiced my graphing techniques to confirm that the gradient is negative. I have a sense of understanding of the question and a feeling that my answer is most likely correct. So I'm always looking for ways in which students can deepen their understanding in mathematics. Out of just one basic question like this, we can do multiple things and strengthen our areas, all of our areas of mathematics. So there's an example. The better you can get at graphing like that, the better an idea you've got of things being, effective or working or not, that your answers are reasonable. So I would always encourage to consider trying to graph things as much as possible. The alternative, if you're really struggling with that, is whack it in Desmos, see what it looks like, see that it makes some sort of sense of what sort of gradient that you've got. All right, so good luck doing those quotient rule questions. This one's a pretty tricky one, has multiple steps inside it with the root x and the x squared minus 1 down the bottom. I haven't been including any that require a chain rule. We'll be doing that in the next video, but you can even have chain rules inside of quotient rules and it can get really complex, but we'll look at some of those in the future. That one was complex enough for today.